Hey, do you know what this is? This is a single-phase electric utility transformer. Your local electric utility uses these to convert the primary electric voltage they use in their distribution system to the secondary voltages you use in your home. If you look around, you might find one of these outside your home or nearby in your neighborhood. If not, you probably have one that looks like that. That does exactly the same thing. Let me show you how these work. Let's take a look at a single-phase electric distribution transformer and see how these things work. We'll start with a single sheet of thin silicon steel shaped like this square ring. On top of this, we'll laminate several more sheets of steel. This forms the iron core of the transformer. We then form the primary winding by wrapping the iron core with 10,000 coils of enameled copper wire, leaving the tails of the copper wire extending upward. These become the primary leads. We'll then create the secondary winding by wrapping another 200 coils of copper wire around the other side of the core, also leaving the ends of the wire extending outward. These become the secondary leads. You'll notice that with 200 coils of copper wire on the secondary winding and 10,000 coils on the primary winding, we end up with a coil ratio of 50:1. When a primary distribution voltage of, say, 12,000 volts from an alternating current source is applied to the primary leads, an alternating magnetic field is created within the iron core. And because of the voodoo relationship between alternating current and magnetic fields, electrical energy is transferred from the primary winding to the secondary winding in proportion to the coil ratio. What that means is that when a primary voltage of 12,000 volts is applied, we end up with a secondary voltage that is 12,000 volts times the coil ratio of 1/50th, which in this case gives 240 volts. A third secondary lead is attached to the middle of the secondary winding. This is sometimes called a center tap. Located in the middle of the winding, the center tap produces another secondary voltage that is exactly 1/2 of the voltage between the outer leads. If the voltage between the outer leads is 240 volts, the voltage between either of the outer leads and the center tap is 120 volts. So what does all this mean? It means that this electric transformer is able to provide two different voltages. The outer leads on the ends of the secondary winding are typically referred to as phases and usually designated as X phase and Y phase. The phase-to-phase voltage potential between X phase and Y phase is 240 volts. The center tap is referred to as the neutral and is designated with the letter N. The phase-to-neutral voltage potential is 120 volts. The neutral is sometimes referred to as the common because when it's connected with either of the phase wires, it produces a common voltage of 120 volts. In fact, 120 and 240 volts are the standard residential electric voltages throughout the United States. Before we move on, let's look at the voltage on the primary leads for a second. The 12,000 volts shown is an example of an electric utility's distribution system voltage. However, it's not the only distribution voltage that utilities use. In some older areas, utilities still use a 4,000 volt system. 12,000 volts is pretty common, as well as 15, 25, 35,000 volts, and even more. The electric transformers used by most utilities are generally exactly the same, the only difference being the coil ratio between the primary and secondary windings. By using the transformer with the proper coil ratio, utilities are able to transform any of the distribution voltages into the standard residential voltages of 120 and 240 volts. Once this is assembled and tested, it's put into a steel tank. When it's in use, the electric current flowing through the windings will generate a lot of heat. So the tank is filled with mineral oil to help dissipate the heat and keep the whole thing cool. The 400 to 700 pound transformer is then hoisted up and hung on a utility pole by a line worker. The primary leads are connected to the utility's high voltage electric distribution conductors. Low voltage cables are connected to the secondary leads, X phase, Y phase, and the neutral. The three cables connected to the secondary leads are the service conductors that are connected to the home's meter panel. If the home has an overhead service, you'll see the overhead transformer attached to a nearby pole. The three-conductor service is extended from the pole and connected to what's called the weatherhead. The weatherhead is located near the roof and just above the meter panel. For homes that have an underground service, you'll see the pad-mounted transformer located somewhere in the neighborhood, maybe even in front of the house. The three-conductor service is extended through underground conduits and connected to the meter panel from the bottom. All three service conductors are connected to the home's meter panel, X phase, Y phase, and the neutral. Copper bus bars installed in the meter panel carry the electric current through the meter and allow the electric utility to monitor power consumption. Another set of three conductors are extended from the meter panel to the distribution panel. This is also known as the service panel, the breaker box, or if you're over 60, it's called the fuse box. It's probably located in the garage, the basement, or behind the door in the spare bedroom. About half of the electric outlets in the home are connected to the X phase and the neutral. You'll recall that connecting one of the phases and the neutral provides 120 volt power. The other half of the outlets in the home are connected to the Y phase and the neutral. This helps balance the load on the distribution panel and the transformer windings. All of the lighting, the kitchen appliances, the televisions, and the ceiling fans are all provided 120 volt power by connecting to one of the phases and the neutral in the distribution panel. In some homes, you may see a strange outlet that looks like this one, maybe in the garage or in the kitchen. This is a 240 volt outlet. Power is provided to this by connecting it to both X phase and Y phase. Larger home appliances that use 240 volt power are connected in a similar way, including dishwashers, electric water heaters, air conditioners, and maybe even the refrigerator. All of that is made possible because of one of these. But before we go, let's take a look at this one. This is the pad-mounted transformer we looked at during the beginning of this video. It works exactly the same as the overhead version. The utility's electric distribution cables are connected to the primary leads, known as bushings. The secondary leads are located on the other side, X phase, Y phase, and the neutral. A single transformer like this one can provide power to a single home or up to 20 homes. Take a look around your neighborhood and see if you can find yours. Pretty cool, huh? Now you know. Thanks for watching.